squared over r hat. They're both r hats, so we can divide the r hats both out. Okay. We know, though, that the r component of the tension is going to be t times sine theta, right? So by using this angle, we can abstract out the bigger picture here and figure out what's going on. So if the tension is equal to t sine theta, and that must be equal to mv squared over r. If we define our direction as inward, we know these are both heading in the same direction. If you use a negative angle, you get the same answer, but we'll assume a positive angle and call those the same direction, so we don't have to worry about it. In that case, we're making some progress here. Furthermore, we know what the tension is because we calculated it. That total tension is constrained by the gravity. So that's equal to mg over cosine theta times sine theta. Right? So that's t times sine theta. All right? Interesting. All right, we're making some progress here. Now we can at least cross off the masses. It doesn't matter what the mass is because the gravity is affecting both the force of the centripetal force and the gravitational force. Those masses drop, so we don't have to explicitly keep track of the mass. It doesn't actually matter what the mass is, what angle this thing is going to end up at as a function of how fast it's going. So let's go ahead and plug in one more value we know. The radius of the circle. The radius of this circle here is going to be equal to the length of the string times sine theta again. So let's go ahead and plug that in. In that case, the length, if we plug in that r is equal to L times sine theta, plug that in here. I'm going to have to go to a new page. The old equation we ended up with was that v squared over r was equal to g sine theta over cosine theta. And we're plugging in r equals L sine theta. We end up with v squared over L sine theta is equal to g sine theta over cosine theta. Okay, so let's go ahead and calculate. Ultimately, let's try to find what velocity we need, say, in order to figure out what. If say we wanted to have that thing turning in a given circle of a given radius, say we know that this length is some length L, and we want this to be some length R that we don't yet know, or that we do know. Say let's set it. We want it to be 1 meter or something, right? In that case, let's solve for what velocity we would need in order to do that. Just solve both sides for v. First I'll multiply both sides by L sine theta. V squared is now equal to L times G times sine squared theta over cosine theta. Take the square root of both sides. The velocity needs to be equal to the square root of L times G over cosine theta times sine theta, right? Because that's square root of the sine squared is going to just be 1. Okay, well, great. That's an equation. What does it mean? Let's think about it. First of all, it means that if you want a longer string, right? As the string gets longer here, the velocity that you need to move it goes up, right? So if you want this in a 1 meter circle, the velocity actually needs to go faster if you start at L. Wait a minute, that doesn't make sense, right? Because that velocity needs to be about the same in either case. It's the angle that's changing as well, right? If L and sine theta are both changing. Okay, so we're not fixing r here. If you fix theta instead, the way I've done it, which is different than my notes, that's on me. So if you fix theta, so you want this to be a 30-degree angle or something, right? If you hold theta fixed, then the longer the string is, the faster you need to spin that thing, and basically it needs to go as the square root. So if you have a string that's twice as long, you need to swing it 40% faster, square root 2 faster. It's also proportional to the gravity. So because the gravity was setting the angle from the beginning, right, by the vertical components needing to match. So in that case, in order to get the gravity to offset itself, you wouldn't have to spin this thing as fast if you're doing it on the moon, say, right? G would be smaller by a factor of 6. The velocity you'd have to swing it would be commensurately also smaller by a factor of the square root of 6. So 2.5 times smaller or something. The function of the angle theta, though, is a little bit non-trivial, right? It's a little bit tricky. First of all, notice that in the case where theta were, say you set it to 0, right, then this becomes a trivial answer. Sine theta is 0, you don't have to spin it at all, right? If it's just sitting there, technically it's moving in a circle of size 0, nothing's going on. If you set theta to 90, what happens? Well, then this equation gets very upset with you. Sine of 90, of course, is 1, so that's no problem. Cosine 90 is 0, and that's in the denominator, and we just divided by 0. That is impossible. What this is telling you is that it is impossible under any gravitational field where g is greater than 0 for you to spin this thing in a perfectly horizontal circle. There must be some component of theta that's in the vertical direction in order to be able to compensate for that gravity. Remember, if the gravity's pulling down and the only forces on it are horizontal, there's no way that you can ever compensate, and you'd never get a good answer. So that fact that the math works out funny there, and it gives you an answer that comes up infinity, or undefined in that case, is telling you something. In this case, it's telling you that actually cannot happen. That is completely unphysical. It actually doesn't work that way. No matter how hard you try, you can't spin that thing in a perfectly horizontal, flat plane in a gravitational field. How am I doing on time? Okay, I got like 12 minutes left. Let's do a couple example problems, then we'll call it a day. So this first problem I have is from an old version of the book, chapter 6, problem 15. That is probably not the same problem number as in the modern version of the book, but if you read through, you'll probably find this same problem in a different one. It should be pretty obvious. Because this problem reads, Tarzan, with a mass of 85 kilograms, tries to cross a river by swinging on a vine. The vine is 10 meters long, and his speed at the bottom of the swing, just as he clears the water, will be 8 meters per second, it says. Tarzan does not know that the vine has a breaking strength of 1,000 newtons. And the question is, does he make it across the river safely? All right, so let's do our usual. We're going to draw a picture here. So here's a tree that's holding Tarzan's vine, and here he is swinging across the river. And he's going to swing like this, and here's our river. And it says that his velocity here at the bottom is 8 meters per second. It says that the length of this vine is 10 meters long. That's a pretty long vine. And he says he doesn't know that the total max tension in that line is 1,000 newtons. So the question is, does he make it across safely? How do we solve that problem? We drew a picture. It's a force problem, so what kind of picture do we need? We need a free body diagram. All right, here's our free body diagram of Tarzan. What are the forces acting on him? Well, there's the force of gravity, mg downward. We only care about what the forces are on him at the very bottom here, which is good, because otherwise we'd have to actually figure out how much he was speeding up as he went down. It's complicated. We don't have to deal with that. Good thing. We'll be able to figure that out, although in chapter 8, when we talk about conservation of energy, but that's just a preview. Okay. The other force we know that must be on here is tension. So the total forces on Tarzan are going to be the gravitational force and the tension in the rope. The other thing we know is that from Newton's second law, the net force is equal to ma. In this case, that must be equal to mv squared over r, right? Because at the bottom here, Tarzan is executing circular motion. All the forces are in one direction, and the net force must be in the positive j hat direction. And it must be equal to mv squared over r in order to keep him in this circular motion. So we know then that the sum of the forces is also equal to negative mg j hat plus tension, the magnitude of tension. And we know these are both in the j hat direction. So what we're going to do is we're going to calculate what his total tension is, and we're going to compare that to what we know is the max capable, 1,000, and we're going to see how bad how badly off Tarzan looks. We're going to solve this for t. The total tension is going to be mv squared over r plus mg. All right, let's do that calculation. His mass, oh sorry, I didn't write that down up here. His mass is 85 kilograms. So let's rewrite this as m v squared over r plus g to make my life a little bit easier. So it's going to be 85 kilograms times v squared, 8.0 meters per second, 8.00 in fact, meters per second, times 8.00 meters per second, divided by r, which is 10 meters. Plus 9.81 meters per second squared. Okay. Tension there is going to be 85 kilograms times 64 divided by 10 is 6.4. So the total acceleration he has to undergo here is going to be 6.4 plus 9.81. That's going to be 16.6. Or 6.40. That was 6.40. This is 9.81. So this is actually going to have to be, this is going to gain a sig fig, right? So that was an addition. 9.81 plus 6.40. It's going to give us 16.61 meters per second squared. Multiply those together. 16.6 times 85. Oh man, I'm going to have to do that in my head. Okay, I can do this. That's going to be 850 if it were 10. It's going to be 1275 if it were 15. So this is going to be like 1325 or something, but that has the wrong number of sig figs, doesn't it? That's 4. We only have 3 sig figs here, so this is going to be 1.32-ish times 10 to the 3 newtons. All right, so 1,300 newtons. Bad news for Tarzan. The max strength of that rope, that vine, it said, was 1,000. So according to this calculation, he's going in the drink. Hope there are no alligators in there, otherwise it's going to turn into a horror flick. Not the kind we thought we were watching. Okay, one more quick one, and then we'll let you guys go. The next one says, it's written as number 40, but it says an 0.4 kilogram object is swung in a circular path on a string half a meter long. If its speed is 4 meters per second at the top of the circle, what is the tension in the string there? Okay, so here's some mass m, and that mass has a mass of 0.4 kilograms, we said. And the length of this rope here is equal to, string it says, 0.5 meters. And